Okay, on part two. So I'm going to leave the power model behind, and we're going to pick that up again. There's another model that shows up, and that's called the exponential model. So somewhere on your notes, find a spot to put this on. And the exponential model looks like this. So notice in the power model, we had the exponent, the variable, which is x. It turned out looking like a star. Our variable x for the power model was down in where the b is on this one. So now the exponent actually contains the variable. So when the exponent has the x in it, it's the exponential model. So let's wax mathematical a little bit. I mentioned yesterday that sometimes logarithms will be used to straighten out curved data. So let's see how that would actually work for an exponential model. We often use logs when we want to get an unknown down out of the exponent. So I'm going to take the ln, that's the natural log of both sides. And when I do that, I've learned in the past that when you have the log of two things that are multiplied, you can write them as two individual logs added. So that's a rule of logarithms that you have been taught. And then also another rule of logarithms allows an exponent to come down and be a coefficient. So I'll bring that x down. So that's why we use logarithms, because those rules allow us to simplify. So we end up with the ln of our variable y, ln of a is a constant, the natural log of a constant is just a constant. So I'll call it c. And then we have ln of, I'll call that first constant. ln of b is also a constant. And then we have x. So notice at the end, when I started with this exponential model, I ended up with only one logarithm in the expression. So sometimes we can take data and straighten it out by using one logarithm. And so we're going to look at the next example on your handout, and it's about the computer chips. So it turns out in this scenario, we have the idea that a number of transistors can be put on a chip, and that number goes up as our technology increases. So if we look at how many transistors could be on a chip years since 1970. So in 1970 we would have very few that we could put on a chip. And then it grew a little bit, but then it went zinging up. So it had an exponential growth in our ability to put chips on a number of transistors on a chip. So we want to straighten that, and it turns out that the way we straighten it is we're going to take the ln of this number of transistors. Number of transistors, and we're going to leave this data, the years since 1970, we're going to leave that by itself, and sure enough, it straightens right out. Let's look at the mini tab to get the lowdown on that. So it's on the next page there, and you can see how it straightened out quite well. So what is the equation that relates these variables now? So go to your mini tab and see if you can pick out the numbers. Notice that the expression, and the way I can tell on this is they put ln right there. So they used ln on the y value and they left the x value the same. So I'm going to do the same thing with the numbers. So I'm going to say ln of y equals some value a plus bx. So now I need to grab these numbers from Minitab. So I get ln of y, and I'll give it the meaning number of transistors. equals A, and I grab A from Minitab, it's 7.06 plus, I just cut it off for convenience, round it somewhat, plus, and then the slope is 0.366, I'll say. And that is going to be years since 1970. All right, so there is the relationship that will straighten out our data, and we can use that model to predict. So let's do that. Let's predict. And what's the S on this one? So see if it has a decent one. S is 0.5. So that's the average difference between the predicting line. So the average S is the average, I'm having trouble saying this again, it's the average that the prediction will be off by 0.5. So that's not a very big one, so we're very happy with that. So let's use the model to predict the number of chips in 2020. So how many, not number of chips, the number of transistors on a chip on 2020. So just plug in, so we have ln, number of transistors, equals 7.06 plus 0.366. And what will we put in for years? So it's going to be the years since 1970. So I have to subtract that. And what's that come out to be? It looks like 50. So I put a 50 in for years. Then I calculate on the right. I get ln number of transistors equals 25.36 when I use the full decimals. Alright, so now you have to remember how to peel off this ln. So this is base E, and remember how logarithms work? So in your thoughts, you know that log to the base 10 of 100 is 2. So you can rewrite that as 10 raised to the 2 is 100. And that's the relationship between exponents and logarithmic statements. So we can rewrite this in exponential form by saying e raised to this number is this number. So e raised to the 25.36 equals the number of transistors that will fit on a chip. So e to the 25.36 is a pretty big number, I guess. I think I wrote down 1.03 times 10 to the something. Is it 4? You can check me on that. Transistors will fit on the chip in the year 2020 if we use this predictor. And our S is fine. However, they did have us look at the residual plot, and it looks pretty bad in that we were hoping for the same, like an equal scattering around of the data, but here's how they got around it, so you'll love this. Notice from here to here, which shows some scattering, this is the highest difference here, is really on this scale. The difference is really only 1. So from here to here is 1. What's the difference on this scale when we see the most scatter over here is negative 1.3? Alright, so at the most. So they're saying even though it looks like a large random scattering with a lot of variance, the true variance is less than 1.3. So therefore they say it's okay to use. Alright. Sounds a little lame to me too. But, alright, I just present that to you. Alright, so let me see what follows. I think I'll shut down and do the last model in a minute.